Okay, now let's implement a burn and a mint function, both for our stablecoin and for our depositor coin. Both of those functions will be required to actually create new stablecoins or new depositor coins with minting, or to destroy them again, which is the burning functionality. And we've actually implemented a mint function before when we were testing our ERC20. If you remember, this was this internal function here with mint, which we were calling in the constructor. And now let's just copy paste this. And implement a burn function that looks very similar. So basically in the burn, we say from amount, and we also don't allow burning from the 0 address again, because it doesn't make any sense to call it with address 0. And then obviously instead of plus, we have minus here. And for good measures, we actually emit an event that says we're transferring the tokens to the 0 address. Of course, we're not actually transferring it to the 0 address, but this is kind of the convention now when you're burning, that you're emitting a transfer event to the 0 address. And yes, if you remember the last chapter with the checked arithmetic, we actually have now integrated underflow support here. So if the balance here of the user is actually not enough for this burn, it would automatically revert the transaction, because this is a normal subtraction and not an unchecked subtraction. Okay, so we can use now this mint and burn function. Let's start with our depositor coin, because it will be a little bit easier to implement. So here, let's start and we actually create a mint function that is 2 and the amount. And it will only be external. And of course, we said the owner of this contract here is the stablecoin, and only the stablecoin is actually allowed to have this capability here of minting and burning. So first, we'll check that the msg.sender, which will in this case actually be the stablecoin contract, not an externally owned account, but a contract, because of course contracts can call other contracts. So the msg.sender here has to be the owner, and if it's not, we just say depositor coin symbol only owner can mint. And if that is all good, then we can just call the mint function. And the mint, if you remember, is internal function. So if we're inheriting here, we do have access to this mint function. So then it's a 2 and amount. And that's already it for the depositor coin. Let's save it. And now let's just copy it again, paste it, and do the same for the burn, because it's essentially the same thing. Except we're saying only burn from, and here of course we also call the also internal burn function. And that's the mint and burn now implemented for the depositor coin. Let's now go to the stablecoin and let's implement the mint function. So this mint function will be the one that people are using to deposit Ether into the contract and in return get actually the stablecoin. So this will be mint. And then because they are depositing Ether, we have to declare it as payable. So now, of course, for one, we can just call the internal mint function again to the sender. And we mint an amount. Let's just call mint stablecoin amount. So how do we get this mint stablecoin amount? Well, first of all, let's declare it. And then we use the amount of Ether that he sent, so msg.value. And now it would be times the price of Ether in US dollar, because our stablecoin is pegged to the US dollar. So it's basically ETH in USD price. So this will be the price of Ether in US dollar. So how do we actually get that price? We'll discuss this later. For now, let's just assume we have it stored. So let's just put it here and say it's a private variable that is worth 2000. So let's just say this is the price right now, and we'll figure out how to actually get this later. And so this is the amount that a person gets minted. Let's save it in format. And now, of course, remember, we also said that there will be a fee for minting. So we'll actually implement a fee quickly here. We'll use a private function, get fee, that we'll implement in a second with the passed value. So to figure out what the actual fee is that the minter or depositor here is paying. And then the remaining ETH will be whatever is left after you subtract the fee. And then we'll use this here to calculate the amount of stablecoin that he will receive. So now to implement the get fee function, we'll create a private view function called get fee, which takes in the amount of Ether and then private view and returns the fee. And now we can return, and we'll need some kind of fee percentage that actually tells us a rate for how much people are supposed to pay as a fee. So, I mean, let's just first assume it's just there as fee rate percentage. And then times the ETH amount. And because it's a percentage, we divide it by 100 in the end. And again, always multiply first and then divide later to avoid any precision loss. And then we'll also actually add a little functionality here that checks if there are already any depositors for the depositor coin, because those will be the ones actually receiving the fee. So we'll convert the contract depositor coin into an address, and we'll check if it's a 0 address, because if it's a 0 address, it means it wasn't deployed yet, and we'll know, okay, there were not any depositors yet. And also we'll just make sure that depositor coin total supply is more than 0, which should always be the case, but let's just add it here. And then if it doesn't have any depositors, well, then for now we just say you don't have to pay any fee because there's no depositors. So the first people who are calling the mint won't actually have to pay any fee. So let's save it. And now let's also add the fee percentage here. And let's add the missing semicolon that we forgot to add here. And now this fee rate percentage here, let's just say that the person who's deploying the stablecoin contract can define this rate. So we'll pass it in the constructor here. And then of course we need it as an actual state variable. We can make it public so it's easy to read from the outside. And then in here, we can actually set it. And yes, of course, this here is in capital because we're not changing it right now. So just so that this is not complaining here, let's just make it constant for now. We are going to change it later anyway. And now let's implement the burn function. And the cool thing about this here is because we are all operating in the same token contract here, we don't actually have to transfer any stable coins for this burning. We can just burn it directly. So someone will just pass in the amount, burn stablecoin amount, and it's an external function, not payable, because we're doing the opposite right here. We're burning the stablecoin. So we can just call burn directly here from the sender. And if he doesn't actually have enough funds, this burn here, of course, would revert and burn stablecoin amount. And now we have to calculate how much ETH he's getting. So refunding him now his ETH. And that would be the burn stablecoin amount divided by the price, which is this ETH in USD. And then, of course, also for burning, we'll add a fee here. So the fee from get fee refunding ETH. And now we'll transfer him the amount, which is the fee subtracted here. So remaining refunding ETH is the refunding ETH minus the fee. And now we'll use this call functionality that we've used many times before. So msg.sender.call, and we'll send him the amount of ETH back here minus the fee. And empty data because we're just sending ETH to his address. So yeah, let's check that this transfer was successful. And if not, run refund transaction failed. All right, so now we have minting and burning implemented. And let's add the semicolon here. And oh yes, avoid low-level calls is another. We can add this to our Sol hint to ignore because we want to use this call functionality here. And now we have a mint and a burn functionality for both the stablecoin and the depositor coin.